Hello friends, welcome to lecture number 10 of electricity and magnetism. So here we're going to discuss about complex reactance and impedance. Okay, so you are I think familiar with these two terms if you have watched the last video. So I have given the link of the previous lectures in the description box. Okay, if you want to watch then you may go through. So before we start, please subscribe to the channel, share with your friends, and if you like the video then hit the thumbs up button. Also hit the bell icon so that you get notified, right? So stay connected. So now let's start. So now you see, if you are familiar with the complex number, so let me draw this axis. So this is called real axis, this x-axis is called real axis, and this is called imaginary axis. So now you see, suppose if you have a complex number z is equal to a plus ib, right, where I is a complex number, I is equal to root over minus 1. I hope you know these things. But in case of electricity in this paper, as we used to denote current also by using I, that's why instead of I we're going to use J, right? We're going to use the symbol J for complex number. So here J will be equal to root over minus 1, right? So then this magnitude of Z, that means this complex number, is given by root over a square plus b square, right? So if you plot here, this is suppose a and this is b, right? A, b. So then this is your small r, this is suppose theta, right, which is equal to small r is equal to mod of z, that is the magnitude of z, is equal to root over a square plus b square, right? Now if you express this in polar form, right, if you express this in polar form, you can write z is equal to r cos theta plus j sin theta, right? You can write that way, taking a is equal to r cos theta and b is equal to r sin theta, right? If you, that means squaring and adding these two, we will get this term, r is equal to this, right? So hope you have understood this. So now you see, suppose if you have a EMF source, alternating EMF source, that is E is equal to E naught sin omega t. Suppose you have this, right? Now you see, if you draw a phasor diagram and if you compare with this diagram, right, then what you will get, you can see this is your phasor, right? This is E naught, right? This is E naught, and this is the phase. Here you see, if you take phase 0, then at time t, this will be the angle omega t, right? And this component is given by this. If you take this one as imaginary axis, this component is E naught sin omega t, right? Now this complex number z is equal to a plus jb. This can be written as z is equal to r, so this form, right? R is equal to e to the power I theta. So e to the power I theta means what? E to the power I theta. So e to the power I theta is equal to, so if you take j here, as we are taking j, small j, so e to the power j theta, right? E to the power j theta will be equal to cos theta plus j sin theta, right? J sin theta. So now you see, you can write this one in complex form. In complex form as E is equal to E naught cos theta, here we're gonna write omega t, plus E naught j E naught sin omega t, which is gonna be equal to E naught e to the power I omega t, right? So here you can see we're gonna take only this sine omega t. Here the source is sine omega t, so we can write this one as E naught I omega t, because we are taking this E is equal to E naught sine omega t. So this can be written in this form, like this way, right? So here instead of I, we're going to use j. We are going to use j, right? So we are not going to consider this. So hope you have understood this. So now you see, let me go to the next slide. So what we have written here, E is equal to E naught sine omega t, which is equal to E naught e to the power j omega t for capacitor just wait, let me adjust a little bit. Let me take that way. Let us suppose so here this is an alternating EMF we have taken in complex form. So then for capacitor, as we have already discussed in previous lecture, that I is equal to I naught, here current leads, right, sine omega t plus pi by 2, right? Compared to EMF, that is E is equal to E naught sine omega t, right? So here you see, in this case, actually let me write this one below. Here you see, for capacitor, for the circuit with capacitor only, so we have already got that I is equal to omega c E naught sine omega plus pi by 2, where this is nothing but I naught, right? Okay, so we can write I naught is equal to omega c E naught, so where E naught by I naught, that's gonna give you reactance, that is 1 by omega c, which is represented by xc, right? So capacitive reactance. Okay, so this is in real form, not in complex form. So for complex form, right, for complex form, that you can write this you can write this equation as this way, right? I naught e to the power j omega t plus pi by 2, right? So when you have sine omega t only, then you can write e to the power j omega t. So now we have sine omega t plus pi by 2. That's why where we are writing here e to the power j omega t plus pi by 2, and this is this e naught. This is e naught e to the power j omega t, right? Now you see, just let me write it separately. Just wait. For complex form, I naught is equal to I is equal to I naught e to the power j omega t plus pi by 2, and e is equal to e naught e to the power j omega t. We can write that way. So now, our capacitive reactance, that is E by I, will be given by E naught j omega t by I naught e to the power j omega t plus pi by 2. That's what we will get, right? So here you see E naught e to the power j omega t divided by I naught. So this can be written in this way: e to the power j omega t into e to the power j pi by 2. We can write that way, because when you have a to the power m, you can write if you have a to the power m plus n, then you can write a to the power m into a to the power n, right? So we have used that identity. So then this two cancels. So E naught by I naught, that is nothing but xc, this one, and here e to the power j pi by 2. So here it will be e to the power minus j pi by 2. So which also can be written as omega c is nothing but 1 by this xc is nothing but 1 by omega c. That's why you can write this one as so. Let me go to next slide. Okay, so here is the last result that we have got. So if you use this e to the power I theta is equal to cos theta plus I sin theta. So instead of I, we have j here. So in that case, so if you have minus here, then this sign will be minus. So if we use that, then what we can write here? You can say we can write e by I is equal to xc, that will be into cos pi by 2 here. So instead of theta, we have pi by 2 now, minus j sin pi by 2. So let me write it properly. So cos pi by 2 is 0. That is why we have minus j x c, because sin pi by 2 is 1, right? Is 1. So we have this. So xc that we have already got, this is equal to 1 by omega c, that is capacitive reactance. So here we can write minus j by minus j by x c, and if you multiply j here and here also j, then what you will get? We know that j is root over minus 1. If you multiply j into j, that's going to be equal to minus 1. So that's why this j into j minus 1, and we have already minus here, so it's going to be plus 1. So that's why we get, just let me clean this part. So that's why we have got E by I is equal to 1 by j x c, because minus j into j, that's going to give you minus j into j is minus 1, which is equal to plus 1. So hope you got this part. So here you see, just let me clean, this is nothing but complex capacitive reactance, right? This also can be written as 1 by j omega c, right? This is also can be written this way. Just let me adjust. Now let us discuss about impedance. So what do you mean by impedance? So impedance is nothing but it is combination of resistance and reactance. Suppose we have a circuit, RL circuit, suppose. So here resistance and this is inductance. These two are in series in this circuit. Then the impedance, this is RL circuit. So impedance in circuit will be given by Z in complex form. So R plus J omega into L. So if it is a circuit with now you see, so reactance, inductive reactance is given by XL, right? XL in complex form it is J omega L, right? We used to write that. So replace this by J omega L, right? So this is impedance for this circuit. Now its magnitude, its modulus will be given by R square plus omega L square, right? And let us take a circuit. Now let us take. So let me write here. This is complex impedance. Complex impedance for RL circuit. So now let us take a circuit, RC circuit. So let me draw the circuit. This is suppose RC circuit, resistance and a capacitor. So then the impedance Z will be given by in complex form, right? In complex form, that reactance, capacitive reactance is XC, which is given by 1 by J omega C, right? 1 by J omega C, right? So here impedance is a combination of resistance and reactance. Okay, here resistance is R and reactance is XC, which is given by 1 by J omega C, right? So its modulus will be given by root over R square plus 1 by omega square C square. So this is complex impedance for complex impedance for RC circuit, right? So this is the complex form of impedance in RC circuit, and this is the in LC circuit this is the complex impedance, right? And here we have got modulus of Z. So hope you have understood. Now let us take an LCR circuit. Okay, so let's go to, suppose we have a circuit where we have L inductor, capacitor and resistance in series. So this is LCR circuit with alternating source, voltage source. Then here in this case impedance Z will be given by combination of resistance and reactances. Here we will get two reactances, one is capacitive reactance, another is inductive XL minus XC. Here you see it depends on these two. Sometimes it may be XC minus XL depending on their values, right? And so our complex form of this XL, that is J omega L, and that of XC, that is 1 by J omega C, right? So this is the complex impedance for LCR circuit. Complex impedance for LCR circuit. Now let me explain with the help of phasor. So here you see this is the EMF E naught small e to the power J omega t. So let me suppose that, and voltage drop across L is suppose VL, and voltage drop across C suppose VC, and that of that voltage drop across R suppose VR, and total of these three gonna give you E naught, right? Total drop of voltage across these three, that gonna give you E naught, right? That gonna give you E naught. Now you see in case of so let me take the axis here. So when we have studied circuit with resistance only, resistor only, in that case current and voltage VR both are on the same phase, right? Both were on the same phase, right? And in case of this is suppose I naught, right? Let me take that way, I naught, and this is the voltage across resistance R, so they are in the same phase. But in case of circuit, the circuit containing or circuit consisting inductor only, in that case voltage lead, so by 90 degree pi by 2, so from here to there it's pi by 2, so VL will lead I naught by pi by 2, so this is VL suppose, and VC lags by 90, right? So voltage lags by 90 degree, so that should be from here to there, again it is 90, so we have written that way. So here you see we can write this as VC. Okay, so now, so here in this case we are considering that VL is greater than VC and VL, that is voltage across the inductor, right? So that's why inductive reactance is written first. In case of VC greater than VL, here we have to write VC minus XC minus XL. So hope we have understood this. Now here you see how to draw the phasor for E naught. Now you see if VL is greater than VC, and now VL and VC are in opposite direction. If you subtract, as VL is greater, then the resultant should be along VL. So this is VL minus VC, right? So now what will be the resultant of VL minus VC and VR? That will be the E naught. That will be the E naught. So here is E naught. This is E naught. So hope you have understood this. This is your E naught, right? You can draw this diagram in terms of XC, XL as well. So let me show you how to do that. So here you see. Let me clean these things. In this axis we're going to take XL, and here we're going to take XC, and this is our R, suppose, right? Then here you see, then this vector, this will be XL minus XC, and here we're gonna get Z, that is the impedance Z, right? And its magnitude will be magnitude of Z will be root over R square plus omega L minus 1 by Z. Sorry, here we're gonna we are not going to write the complex term here. So whole square. So this is the mod of Z. That means length of this vector. So hope you have understood this. Thumbs up button and share with your friends. Subscribe the channel if you are new to my channel, and help and inspire me to create new contents for you and help me to grow my channel. So thank you for watching. See you in the next lecture.